Alright, so let's look at some facts associated with changes, phase changes. Okay. So, if you have a solid turning into a liquid that's melting, right? Typically, you'll see a slight increase in volume, but there's hardly any change in volume actually. Okay, there's some in some case, in certain case, you might like water, and for example, ice turning into water, you actually see a slight decrease in volume. But the key word here is there's a slight change in volume. Okay, so maybe I should just say change here because it could be increase or decrease. Typically, it's increase. Oh, I did say typical there. All right. When you're a liquid, on the other hand, or a solid, turning to a gas, that means evaporation, vaporization, or sublimation. You will observe a very large increase in the volume. Okay, so your gas pretty much fills up your entire container. So, you know, you make a bigger container, you make a bigger change in volume. Now, when you go from a solid to a liquid to a gas, that conversion process is an endothermic process. What does that mean? That means it draws heat from the surroundings. The surroundings must be hotter than, or at least, yeah, must be hotter than the solid, or for it to turn into a liquid, or for a liquid to turn into a gas. So it's an endothermic process. Heat is absorbed. Okay, so endothermic means heat is absorbed. Okay. On the reverse process, on the other hand, if your gas turns into a liquid or a liquid turns into a solid, that process is exothermic. Okay, so solid to liquid to gas, you need to absorb heat. Okay, it's endothermic. So the reverse process, gas to liquid to solid, is an exothermic process. It releases heat. So how do we interpret these facts? First, let's take a look at the volume change. The way you interpret volume change is that you say that in the solids and the liquids, what did we say in the solids and liquids? Yeah, in terms of the change in volume. When a solid turns into a liquid, there's a very slight change in the volume, right? And the reason for that is that atoms are already packed as close together as possible in solids and liquids. So, you know, what we'll see later is that in the liquid, they just have a little bit more movement, but they're still packed as closely as possible, so there is no significant change in volume. Why is there a very large increase in volume when a solid or liquid turns to a gas? The way you would interpret that is this. So the atoms are closely packed together in a solid or a liquid. If they turn into a gas, basically the interpretation there is you just have a spreading out of the atoms or the molecules. If they're grouped into molecules, then the molecules will spread out. Okay? So you have 1, 2, 3, 4, 5, 6, 7, 8 here. So I need to do 1, 2, 3, 4, 5, 6, 7, 8. So that's the interpretation at the atomic level of why when a solid or liquid changes into a gas, there's a large increase in volume. So the atomic interpretation is just a spreading out on the atoms or the molecules. Okay? So exactly how far apart are the molecules in a gas? So if you have like 24.8 liters, 24.8 liter sample of air at room temperature, so let's say you have an empty 2-liter soda bottle. How many of these would you need to get 24.8 liters? To 24.8 divided by 2, that's about 12 and a half. So if you have about 12 of these, okay, all empty, so it's gonna, all those bottles will contain air molecules, okay? If you could count those molecules, you'll learn later that it's going to have this many molecules, 6 times 10 to the 23rd. Okay, so what's 6 times 10 to the 23rd? That's a big number, right? 6 followed by 23 zeros. So how far apart, based on that information, you can figure out more or less, on average, how far apart the molecules are from each other. Okay, and I'll let you work it out. You should find that on average, okay, the molecules are 3.5 nanometers apart. What is a nanometer? A nanometer is 10 to the negative 9. So the prefix nano means 10 to the negative 9. So 3.5 nanometers, that's 3.5 times 10 to the negative 9 meters. Okay, so how do we do this? Okay, imagine we spread them out. We got a big box, 24.8 liters, right? We spread them out even. Imagine you spread them out evenly. So we make little boxes here. And in the middle of that little box is one molecule. Just imagine they're not moving, you spread them out. Okay, so basically what we want to do is, okay, here's a box, and here's a neighboring box that has another molecule. So I've got one molecule here and one molecule there. Okay, so the average distance we say between the molecules would just be this distance from center to center, or that would just be the side. We'll make those boxes cubes to make it easy. So the length of the side of the cube would be the distance. You'll find that to be about 3.5 nanometers. How are we going to do that? Well, let's see. Total volume divided by, how many boxes would we need? 6 times 10 to the 23rd. So the total volume, you divide it by the number of boxes you need, that gives you the volume per box, right? So volume per box is equal to, what was it? 24.8 liters divided by 6.02 times 10 to the 23rd. Okay? Okay. I'm going to change my unit here to make it easier to figure out. A liter is 1,000, so 10 to the 3rd cubic centimeters. Okay? 1 liter is 1,000 milliliter, and a milliliter is a cubic centimeter. So I can write this as 24.8 times 10 to the 3rd cubic centimeters divided by 6.0 times 10 to the 23rd. So let's calculate that. 24.8 times 10 to the 3rd divided by 6 times 10 to the 23rd. And that gives me 4.1 times 10 to the negative 20. 4.13. I'll put an extra significant digit there. So one past the last sig fig. So there should only be 2 sig figs. So 4.13 times 10 to the negative 20 cubic centimeters. So if I know the volume of a cube, what's the side of the cube? If this distance is A, that is A cubed, right? The volume of a cube is, if the length times width times height, A times A times A is A cubed. So what's my A here? So let's take the square root. Cube root. 4.13 times 10 to the negative 20. Is it negative 20?
Yep.
Okay. Negative, and raise it to the power 1/3. I've got a cube root button here, so that makes it easy. Or if you don't have one on your calculator, you raise it to the power 1/3. So raise to the power, parentheses, 1 divided by 3. That's how you take a cube root. Okay. So raise to the power 0.333. And that gives you 3.45. So that's 3.5 times 10 to the negative 7 centimeters. Okay. Now centi is, the prefix centi means 10 to the negative 2. So that's going to be equal to 3.5 times 10 to the negative 7 times 10 to the negative 2 meters. Okay. So centi means 10 to the negative 2. So that gives you, what's 10 to the negative 7 times 10 to the negative 2? 10 to the negative 9. So 3.5 times 10 to the negative 9 meters. So 10 to the negative 9 meters, that is a nanometer. So 3.5 nanometers. Okay? So that's a that would be the average distance between the two molecules, between any pair of molecules. Okay, neighboring molecules in neighboring boxes, if you think of it that way. If you spread them out, just so you get a feel for what the average distance is. Okay. The important thing to realize here is that this number right here, you compare that to the estimated size of the air molecule. Okay, remember we said the estimated size of an atom is what? About 10 to the negative, the diameter is about 10 to the negative 10 meters, right? Typical atom. So if you have a diatomic molecule, oxygen and nitrogen are the molecules you'll find in air. So you have a pair of those. So you're looking at about what, 2 times 10 to the negative 10 meters, right? Or that's about 0.2 nanometers. Okay? So in fact, if you were to just estimate your air molecule as a sphere, it's about 0.6, 0.16, 0.2 nanometers. That's a typical size of your molecule. Okay, I got this from some other experimental information. But anyway, how does 3.5 compare to 0.16? Well, let's calculate that. 3.5 divided by 0.16. That's about 22 times. So it's about 20 times bigger. Okay, so this box right here, so if you have one atom here and the atom here, this is 20 times. If this is 1 unit here, 1 unit here, then this distance is 20 times. So they're very far apart. Okay? And in atomic terms, that's a very large distance. Compared to the size of the molecule itself, the average distance between molecules is very large. Okay. Now, if you did the same calculation for, let's say, as liquid, okay, an 18 milliliter sample of water, okay, is going to have the same number of molecules, 6.0 times 10 to the 23rd. 18 milliliters, that's almost like 4 teaspoons of water. A teaspoon of water is 5 milliliters, so 5 times 4 is 20 milliliters. Okay, so about 4 teaspoons of water, 4 teaspoons of water would have about this many molecules of water. And if you do the similar calculation, I'll leave that up to you to do. Okay, now, since I've shown you how it's done for the other one, you'll find that the average distance is about 0.3 nanometers. What did we have for the other one? 3.5 in the air, right? So they're much closer. And the the estimated size of water molecules, very similar to the size of an air molecule, is about 0.15 nanometer in diameter. So you can see that the distance is only about 2 times the diameter. So they're much closer together in a liquid and in a solid. Okay? So the molecules are as close as can be. Okay? Now, and when that happens, that's why you can hardly change the volume of your solid or liquid. Because if you try to squeeze them further in, as we'll talk about later, okay, what do we know about molecules and atoms? They have charged particles, right? Nuclei and electrons. When you squeeze those as smallest volume into a smaller volume as possible, they start to really repel each other. You can only get them so close. Okay, and so the distance they acquire would be a balance between the distance that's where you see a balance between the repulsions and the attractions. So let's test your understanding. For which of the following are the atoms on average farthest from one another? Air, gasoline, or copper wire? Air, because this is a gas, right? And gasoline is gas, but it's not a gas, it's a liquid. And copper wire is a solid. I got this one. You look at the pictorial representation shown below for a change in physical state at the molecular level. So you have what are called diatomic molecules here, molecules made up of 2 atoms. Okay, the picture best represents which of these changes? Correct, gas or solid or gas or liquid. So this would be condensation. Yes. Thank you.